Hello, my name is Tammy Freeman, and I am the Medical and Biophysics Editor for Physics World. I'd like to welcome you to today's webinar, Machine Learning and Automation in Radiation Oncology. The webinar will be presented by Fredrik Löfman, Head of Machine Learning at RaySearch, and Tom Purdie, Medical Physicist at Princess Margaret Cancer Center. In the first part of the webinar, Fredrik will discuss how RaySearch is pioneering machine learning for smarter and faster oncology software. And in the second part, Tom will talk about automatic treatment planning and machine learning from a clinical perspective. The speakers welcome your questions, so please do send in questions at any time during the webinar using the button on your screen, and we'll try to answer as many questions as possible at the end of the presentation. You can also rate the webinar at any point using the ratings button. Now, I'll hand over to Fredrik.
Okay, great. Thanks, Tammy. So I will speak for the first part of this presentation about machine learning in radiation oncology. So the outline of my talk is to start with some basics about machine learning. Then I will give two examples of machine learning applications in radiation oncology. That is automated organ segmentation and automated treatment planning. I will then have a couple of slides in the end that shows and discuss the potential for machine learning and some challenges that we see when applying machine learning in oncology. So the machine learning department at RaySearch started in 2017 in May, so it's 1.5 years roughly. We have about 10 people working with machine learning, analytics, and big data. And we develop machine learning algorithms and the learning framework for RaySearch products. So that is RayStation and RayCare at the moment. We are working heavily also with research collaborations with clinics and academic institutions. And you may view this department as a prototype factory, so we want to be fast in developing machine learning prototypes that then can go into the products. And through these collaborations, we want to get or incorporate clinical knowledge into the machine learning methods that we develop. Okay, so we go back and look at machine learning. What is machine learning? And it's a very well-used word out there. It's quite hyped, you can say. But this is how we view machine learning. So in a bigger setting, you can view AI, that's artificial intelligence. So that's intelligent behavior of machines. As a subset of that, we view machine learning, which is then AI, but with the ability to learn without being explicitly programmed. And a subset of machine learning can be viewed as deep learning, and that's then kind of the hottest topic in AI today, and that is then where we have neural networks, artificial neural networks. So the important thing about machine learning to remember is that the algorithms are designed to learn from experience or data, and they are trained on data, and that for oncology that can be CT images, RI contours, dose distributions, outcome data. And once you have a machine learning trained model, you can use that and apply it to predict. And this prediction has the ability to generalize to unseen cases. So if we train on a set of CT images, for example, if we get a new CT image in, then we can, this application of the model will generalize to a new patient, and that's specific geometry. So when we look at I have two slides here. The first is about training and the second about prediction. So when training a model, you have the training data, and you have a framework for doing the training, and you have the output, and that is the trained model. So as an example here, we have a cat and dog classifier. So this is often you use, for some reason, animals in this example, so I do it as well. So the training data is then images of dogs and cats, and they are labeled then with the correct label. So the dog image is labeled with dog and the cat with a cat. Then we train this machine learning model. So we feed the dog image into the model, and then this model is optimized to classify this image as the correct output dog. And then we do this with the cat, and then we can also augment the data. So we can, for example, rotate the image, as we have see here, and we learn this network to classify cat. And we augment the data to get more data to train on, but also to get the model to generalize better. And the output then is just a trained model, and that's completely anonymized, and there's no sensitive data in there. So it's very useful, very good then for sharing. Then when we want to apply this model, we then have the model, but we also have some new input data. We have a framework for prediction, and then the output is the predicted output. So with this example, we then feed 3 new images in there. It's a dog, a cat, and a horse. We push them through this machine learning model, and the dog is very easy because that was in the training data. The cat is the same. The horse was not in the training data, and therefore this machine learning model will struggle with this image. So if we generalize to oncology, this means that, for example, if you train a machine learning model for ROI segmentation, only the ROIs that are in the training data will be there when you apply the model and you generate ROIs from this model. So there's no magic. It won't learn properties that is not in the training data, although it will generalize. So now we move on to two examples of where we have applied machine learning for oncology. The first example is automated organ segmentation using deep learning, and this is then available in the RayStation release in December. OER segmentation, I mean, there are other automated solutions out there, such as Atlas-based and model-based segmentation. And I think the main difference with machine learning and deep learning to approach this problem is that it is much faster online. So when you apply the model, it's very fast. And it's also very easy to share. And there are some recent results indicating that the qualities can be very good with deep learning. And the deep learning techniques, we use a 3D unit convolutional neural network, and it's very useful for CT or medical images. And this application, I mean, we're also looking at target delineation, and we are not limited to CT. It can also be MR or other image formats. So if we compare them to the former slides, so here we have the input data is the CT data and the RIs, so the contoured RIs, so typically 50 or 100 patients data here. It could be more, but that's kind of the order what we see. It's useful. We then apply some data augmentation, as I said, rotation, translation, maybe some deformation to generate more data out of this training data. We optimize these neural networks, so there's one for each RI. And out of this, we have a completely then anonymized, no patient data model that can be shared between clinics. So when we want to apply this model, as we see in this slide, we have a new image set. We have a new CT data set. We have the model that we trained, and now we basically push this CT image stack through these networks, and then we will see the 3D meshes of the RIs at the end. So I will try to show this live now in the RayStation application. So I will share my screen, and then I will go to RayStation. See if you can see this. Maybe there's some lag in the... Yeah, I can see on my colleague's screen here that this this screen is, the RayStation is not visible. So, or maybe it's just a question of time lag, sorry. Yeah, so I will basically get going because I think this will pop up. So I will show you a deep learning segmentation of a thorax region. I really hope this comes up because there's a lot of time lag, it seems. Okay, I'll do this and hopefully you see it. So we have RayStation here. I have a thorax case. So I select new RI geometry. I select then deep learning segmentation. I basically have different models here. So I select the thorax model, which has 5 RIs, and then I run it. So sorry if you can't see this. Yeah, maybe I should flip back to the presentation then. Yeah, sorry about that. I'll skip the screens. I'll go back to the presentation. Always something with presentation technology, I guess. So we move on. So the other application we have is automated treatment planning. This is a collaboration with Princess Margaret Cancer Center in Toronto, and this is then also available in RayStation in December. Tom will present more about this in his second part of this talk. But basically, we use machine learning to predict a personalized dose for the patient, and then we generate the treatment plans without manual planning steps. And I think this approach, together with automated RI segmentation, will work really well in this kind of setup of online adaptive. So if we move on to this one and we look at kind of the same framework as before, so the training data now is the CT, the RIs, and the treatment plans with dose distributions. And here we train so-called random forest models, so it's not a deep learning technique, it's more of a classical machine learning technique. And we generate these random forests out of this training data, so the model is basically a collection of random forests. And these are also then completely anonymized. We then apply these automated planning models in this way. So you have a new patient coming into RayStation, you have the CT and you have the RIs. So possibly the RIs were segmented with a deep learning. You then predict the dose using this random forest model, so basically infer the dose on this new geometry and RIs. And this is a full spatial approach. This is very fast then, and then once that is done, so we have kind of the most likely dose distribution for this new patient. We apply a post-optimization in RayStation to make this plan deliverable with respect to the treatment machine that was selected. And Tom will speak a bit more about the clinical results of this, but one thing to mention here is that this approach is very useful because we get a lot of information in this when we apply this machine learning model. So for example, it's very useful for generating multiple plans that are, so we can generate the most likely plan, but we can also generate highly likely dose distributions with certain different trade-offs. And this is a screenshot of this, where we show a head and neck case with 3 different very likely dose distributions, but with some different flavors. So this approach can then, you train, as for the segmentation, you train this model offline. You do it not very often, but maybe every quarter or something. But then once you have this model, maybe you have one for each protocol you have in the clinic, then you can apply it and you can script this. So basically you can script the generation of plants and RIs. So when you start in the morning, you have all the RIs or all the plants ready for you to review. So these were the two kind of applications that we wanted that are the most like the ones that will pop up in the clinic already now in the release in December. But we also work on other topics, and I think there's a lot of kind of applications in machine learning in oncology. But having said that, I think there's also a lot of great algorithms out there that are not machine learning. So we need to kind of focus on to apply machine learning where it can make a difference. And these are some of the projects or topics we look at. It's deep learning for target volume delineation. The image here is from an AAPM poster that we presented. It's a collaboration with MGH, where we use then deep learning to delineate different parts of the brain, and then we can generate the target volume from this. And this is a full 3D approach where we all have 2 MR sets and 1 CT set. We have also applied machine learning to generate synthetic CT from MR. We're looking into decision support. This is more with the RayCare system, so the oncology information system. A challenge here is, of course, the outcome data or toxicity data that is sometimes hard to get a good representative set of enough volume. QA and anomaly detection is another kind of obvious application of machine learning oncology. I mean, we see these kind of applications in other fields such as finance. So I think it's a quite low-hanging fruit. And as I mentioned, online adaptive. But having said that, I mean, machine learning is nothing without data. So in parallel, we work quite heavily with what we call RayAnalytics, which is an oncology data platform. So it's like an analytics visualization platform for learning then in terms of workflows and treatments and the processes in radiation oncology. So we want to avoid each clinic building their own infrastructure for data collection and storage and to support model sharing rather than data sharing of sensitive data. And we hope that this solution will enable researchers and research groups to access clinical data in a structured way and for analyzing that data. Have a couple of prototypes installed at clinics for evaluation at the moment. But I mean, ultimately, we want this to be a useful tool to get more insights from the data at the clinic and to put machine learning into clinical practice. I should say that we will demo all this at Astro that's coming up here in quite a few weeks in San Antonio. So, I mean, how will this work in practice? I think this is, in my view, kind of the current situations where we have research groups, we have vendors, and we have hospitals. And I mean, data is siloed. There's kind of limited knowledge transfer. There may be some variance in the treatment quality and the processes between different clinics, maybe even within the clinics. And there's limited data available. So what I think would be fantastic would to see this instead, where we have kind of data lakes, we have clinic sharing models, so maybe even co-training and machine learning models. I think as a vendor, we need to support this kind of technology that is arising, such as distributed learning, where the machine learning models, they are moved, but the data is not moved, for example. And I think that, I mean, overall, the community would benefit from data sharing across clinics and countries, as more accurate data insights can be made and better machine learning models can be built. And I think machine learning is, I mean, it has a great potential it's a good way of sharing knowledge. So if you have a clinic with a lot of sites, I mean, you could get the same treatment regardless of sites. There can be large clinics that have a lot of knowledge of certain treatment sites that knowledge can be transferred to smaller clinics through machine learning models. So the smaller clinics can generate similar RIs or similar treatment plans as the larger clinics. I got kind of a hidden message here about trying to share the screen again, but I think in terms of time, I think I'll skip that actually, because I would just like to speak for a couple more minutes before handing over to Tom. So there is, of course, there's new technology coming in. Of course, there are considerations and things to discuss here. These are some questions that typically arise, and how much data is needed, and it's typically hard to say, but it is definitely in the order of 50 or 100 patients to train a machine learning model for segmentation, for example. But it's maybe more important to have representative unbiased data. It's more important than having a large volume to avoid bias in the model. How general is a model? Well, for example, the automated planning model should be specific for one treatment site, one modality, and as it's a spatial approach, it should be specific to a dose kind of shape. So maybe it's possible to mix a model across single arc VMAT and 7-beam RMRT, but not if the dose distributions are very, very different, because then that's probably two different machine learning models. What if the training data is not good enough? Well, bad training data will affect the performance negatively. Although there's tricks to do, and we can try to improve the model and detect bad training data. Basically, training a model requires some knowledge and skills. How is a model validated and managed? We believe that a model should kind of have the same approval structure as a treatment machine. So it should be there should be certain roles, training machine learning models, and this person should then be responsible for the training and the model management and model validation. And this would be a very important role at the clinic going forward. Of course, early days when we roll this out, we will support in training models at the clinics. But in the end, this should be driven by the clinics. Will everything be automated? Well, no, it won't. That's not what I think. I think in the near future, there's no need to worry or think about AI or machine learning replacing humans in oncology. I think it's better to view it as a possibility to augment the user's help to make the care more consistent, and I think it's a great way for knowledge transfer. It could also help to free up some time for the professionals to focus on complex cases and maybe more focus on the other challenges, such as where the uncertainties in the process and so on. And finally, deployment of models. Well, I think we should all the vendors should make sure that machine learning models and the deployment process kind of facilitates that clinics can share the models between them. So it should not be tied to a release version of the software. It should kind of be independent of that. It should also be, very easy to deploy new models, because I think this field will develop rapidly, and as more data comes available and new technology is developed, we should have a kind of a fast, robust, and safe way to deploy the new models. So I will want to finish off my part with thanking them, the RaySearch machine learning department, the great people there. Also the automatic planning team at RaySearch, and then of course all the other departments, because machine learning turns out to be, we work with research, development departments, legal, service, sales, everything. It's very cross-department topic. And of course Chris, Tom, and David at Princess Margaret, Roel, Eric, and Hans at Groningen in Holland, who has helped us evaluate planning. So with that, thank you for listening. I'm sorry about the RayStation demo, and I hand over to Tom.
Great. Thanks, Fredrik. So I'm going to talk about specifically automated treatment planning using machine learning. The work I'm going to present is basically the last bit of work that we've been doing on a retrospective clinical validation and how we're moving that into a prospective study. We've had some other publications doing some more technical validation, which Fredrik mentioned on his previous slide, which you can use as a reference. So we've been working on this for quite a while in terms of applying machine learning in radiation oncology. This started in 2012. We have a nice team, both clinical and technical, and we have a bunch of research funding from our foundation and a bunch of external grants in Canada. So I also would like to say we've been doing automated planning for quite a long time. Starting in 2008, we developed an automated treatment planning process for tangent breast planning, which is now or has been in a RayStation as a module for the last several years. So that started in 2008 and is still ongoing. And we've at Princess Margaret treated over 5,000 patients using this method. So more recently, in 2012, we decided to look at machine learning, and that will be the focus of the next 15 minutes. So I'm hoping to run through this pretty quick so we have some time for some questions. I saw a bunch of good questions come up. So here's a 10-second primer on treatment planning and radiotherapy. We image, contour, we add beams, we go through this iterative optimization process, and we then calculate a dose, and then we iterate and iterate. And so what we decided to do was change this paradigm with machine learning because, in effect, we know exactly what the dose distribution is that we want to see, but there's really no nice way in any software to articulate that, aside from, if you had a paintbrush and you can start painting dose on a plan, which would take forever, but it would also be highly inaccurate. So this is something that's really good for machine learning. You could almost think of the application of machine learning here as not doing a segmentation of like a binary mask, like you're contouring a structure, but you're doing many, many segmentations on an image, which all represent different levels of dose. And so what we do in the machine learning paradigm is we take an image, we still rely on contours. Interestingly enough, we don't actually need contours technically. It does solve some problems. It also creates some problems. For all intents and purposes, we'll say that we will need contours at the very least the target. And we just need structures that are important for evaluation. So the nice part of a machine learning paradigm for planning is we don't need to build any structures strictly for planning, either to try to form dose in a particular way or to avoid some certain spots. And through machine learning, based on these two inputs of an image and contour, we basically say this is a predicted dose. From that dose, what we can do is we can infer or we can extract a reasonable beam geometry. And so we just need a beam geometry, and then we can apply mimicking technology, which is commonplace in RayStation, to then make these beams modulated and deliverable, so completely deliverable. And so I would actually say that the last two parts of this process are actually fairly solved problems. Mimicking is demonstrated to be very, very accurate in terms of being able to reproduce one distribution to another. So at the end of the day, what we're trying to do is we're trying to use ML to make a dose distribution or infer dose distribution, and we use this as a spatial dose objective, we call it. So basically, it's as opposed to having to specify dose volume of criteria per ROI, we're taking a look at the entire image, and we're making an objective for the entire image all in one shot. So you don't have to make any specifications at all in terms of weight or any objectives, and there's no, in this process, any iterative or manual steps. So What I was talking about before was a predicted dose, which you would see here on the left, and a mimic dose on the right. So this basically is turning a dose where there's absolutely no plan for the predicted dose, no beams or anything, to the one on the right, which has fully modulated deliverable beams. One of the strengths that we're employing when we're doing automated planning is we're trying to find a similar patient between a patient we're planning, like a novel patient, say, for example, the one patient on the left, with a patient that we have in a database. And so you might ask yourself, what is a similar patient and what does that look like? And you could potentially argue that these patients are very similar, and although it's not delineated on the right-hand side, you can see a little bit of a seroma. I don't think my pointer works. But you can see that these patients are in a similar size. They have a similar relationship between, say, the lung distance and the cavities. They have a similar size of the whole breast target. And a patient like this, you might argue, is being very different. But how do you articulate that? Because that's very important moving forward, and that's one of the major technical challenges of applying ML. So when we think about trying to do this matching, it's very easy for us, like a human, to go back and say that these two things are different. That was very easy from the example on the previous slide. But what that entails for a computer is actually much more complicated, and we need to do a lot of work in order to make that connection between similarity. And so what we want to do is we want to look at how dose is placed on multiple scales. And so what we see here is, maybe I make this big box, and this doesn't really tell me too much of about the patient specifically, down to a very specific level of what we want to, where we want to put dose. But what we want to do is we want to hone down on certain specific parts of the patient and then extract features on different components, or like effectively like patches of the patient, if you will. And then we need to use these type of patches to make these similarity scores. So you can see here that if I just took a look at the patch on the bottom left versus the bottom right, these are actually very similar in terms of both density and some shape, but they're very different. In one case, we don't care about what is happening on the one on the right, for example, because this is not an area we're actually giving any dose. So when we start ripping features and using this for similarity, we want to only use the features or spatial locations in the patient that are relevant. And so that, in this case, would be the one on the left, for example. But we still need to get around to telling the computer which is important. So said a different way, you could also look at it by taking the image, and then on the left here as an example, and then what we can do is we can start taking a look at segmenting this image, basically looking at areas of homogeneous dose. So you could think in a structure of a random forest that Fredrik was mentioning. We could take a look at the end leaf from the forest, and we can say, and we can start coloring an image, for example. And so each color here would represent a different leaf and representing a different dose. And so based on some image similar to this, if say we took a look at, say, two features, which is shown on the right-hand image, and we're trying to relate how these features are able to predict dose for a patient, or which features are important for predicting dose, then we can generate this like density encoding as an example. Now, that's for one patient. So we can do it for a different patient, and you can see for this patient, we have the cavity, which is the yellow contour, is in a very different location, even though the breast volume, outlined in green, is very similar. And you could also argue maybe the lung volumes are similar. But this patient has a very different density encoding, and so you would not want to use this top patient for predicting dose for a bottom patient. And so this is built into the system to basically prioritize what parts of the image are relevant for predicting dose. And then we can use that to make better predictions, of course. One thing that always comes up about trying to find patient matches when we talk about them is always knowing the number of patients we need and that we need to train on. And so I think the universal answer here is there is no way to absolutely know how many patients you need, and typically more patients are better, but within a certain limit. And so what we did was we took a look at the ability to match two patients using again, probably a terrible metric because it's too strict, but we use the gamma metric to try to compare two dose distributions and how well one patient can predict for another. And so we increase the number of atlases, or the number of patients in the database. So this is on the x-axis. The y-axis is basically the gamma accuracy score. And what we can see is that in 3 different cases, we did whole breast, breast cavity, prostate, that these are basically asymptoting at about 20 cases. And you can see that what this is showing you is that if you have very, very few samples, your accuracy is going to be very low, and then you're going to get diminishing returns as you start adding some. So based on this, can you infer that you only need 40 or 50 patients? Well, I guess the short answer is absolutely not, in the sense that if you still only have a small set of patients, then you're limited to the variation within that group. And so having more patients gives you more flexibility to be able to handle more outlier cases. What is interesting, though, and it might be a little bit difficult to see, but you can see the black lines are the mean values. What is really interesting here in the case of the prostate is that the low value, the lowest value for any one patient is actually still pretty high. So it's not close to the mean, but what this is implying is that the patients are close enough that even with a few number of samples, the minimum matching is actually pretty good. We don't see this in breast, but you could argue that this, again, is very expected because in the case of treating breast, you could have a seroma anywhere in the breast, and there's a much larger variation in, say, breast size that would account for you needing to have more samples in order to make a better prediction. So let's, I'll finish up by talking about this really cool retrospective study we did. So what we did was we did a clinical validation of prostate VMAT automated planning in our clinic. We started with 116 patients. So we took them out of the database. Then we realized that some had some missing contours, so then our data set shrunk a little bit. And then from that, we took 20 cases out that we planned to test on, and then the remaining ones we did training on. So subsequent to that, we also recognized, and this was I guess bad luck because we don't typically have more than 10% of our patients with hip implants, but 3 of the 20 patients we selected actually had hip implants. And so we actually excluded those for the study because we know that the distributions for patients with hip implants are substantially different than those from like normal patients without. And so the only reason I bring this up is that this actually really highlights the need for being able to be very rigorous with the data that you have, and trying to match the problem for using the right technology. So if we tried to plan these cases, they would have been terrible, but that would be unexpected. That would be expected because we're not actually training them on a real data set. So this was very enlightening as we went along, but at the end of the day, we recognized that this wouldn't be fair to include. And so at the end of this, we were left with 17 patients we evaluated. And so in this study was really great. We had 2 radiation oncologists who specialize in GU, and we had a GU medical physicist score all these 17 plans, first of all, independently. And so what we were taking a look at was the approval rating, whether or not the plans were acceptable from a target coverage, sparing, conformity, symmetry, overall acceptability point of view. And we can see here that they're all really high across the board. The automated in blue and the clinical plans are in green. This becomes a little bit easier when we start taking a look at the differences. So this is the same data from the previous graph, just looking at differences. And what we really found out was automated plans were deemed to have a higher approval rating from the reviewers, again, independently, for both target coverage and OAR sparing. And where automated planning did a little bit worse was in terms of the high dose conformity. So the dose, I guess, may not have been as high, or some of the more softer dose evaluations like the gradient or the symmetry. What was interesting is that we had the same number of plans acceptable. So in fact, one of the automated plans generated was deemed unacceptable by 2 reviewers, and two clinical plans were deemed unacceptable by each one reviewer. So they had the same number of the total number of reviews as being unacceptable. Then we decided to do this head-to-head where the reviewers could actually see like an A and B plan beside each other. They were able to look at the dose distribution straight up and be able to compare, say, both deviations and dose differences at the same time. And then we did this analysis. And so what was interesting here is when we looked at them straight up, automated plans were preferred 74% of the time, equivalent in 20% of the time, and only 6% of the time was the clinical plan preferred. So these results, completely blew us away because we were definitely going to be happy with around like a coin toss between the two, but that's not exactly what happened. And so these were for overall scores across all 51 reviewers. When we take a look at the patients, so what we did was we took a majority vote. So if two people preferred automated versus one, then we considered that a win for automated. And what we found out that of the 17 patients, 12 patients were preferred by majority rule, and 3 were again equivalent. Interestingly, of the 17 patients, 10 patients had a consensus review positive for automated, and so meaning all 3 reviewers preferred automated. So again, too, that's very interesting. And so what we're driving at is that through the idea of using these atlases, and the dose mimicking, we're able to extract the best features from a number of patients, not just one patient. And so we think this is a strength of the methodology to leverage some of the best parts of the distribution from a sample of patients and use that when we're doing our prediction, which is helping here. So that was that study. As I said, all of our previous work has been published. This is the only work that is currently under review, and so hopefully you'll see this sometime soon. But we have a bunch of other work, more looking at technical validation, both in sites like prostate bed, rectum, and we have a more recent paper on oropharynx, but I won't talk about those. What I think is now the next step in the evolution of our validation here is to do a prospective study. And so, in fact, we have already treated 2 patients using machine learning-based plans at our center. And so this has been a relatively new endeavor, but we're going to start a formal prospective study where we want to take a look at how ML is impacting the process in the treatment planning. And so I'll just quickly run through 3 steps here. We're doing a retrospective ML study again. So this is similar to what we did before. And so this is going to be able to basically figure out what is our machine learning clinical acceptability baseline. Then we want to start looking at, and so this is done retrospectively. So the people actually making the plans, the planners, the symmetrists don't actually know we're doing this. The next part of this process is to actually tell them that they're going head-to-head with a machine, and we're gonna see if there's a change in the baseline with the humans being aware that they're now being compared to something. So this will basically figure out, are we changing practice simply by having humans know that they're being compared with something else. And the third part, which I think is really interesting, and this will be something that will be available in RayStation on some level, and that is to have multiple plans available through machine learning. So we can tweak different parameters to generate different plans based on the same native data, and then have the human be able to select from maybe a couple or several plans and see if that is actually a better result. And so we think that this human ML cooperation is going to be really interesting, and we're hoping we'll actually produce the most clinically acceptable plans. But this is something we just started, and we're looking forward to getting some results for this in the next year or so. So just to wrap up, here's my last slide. We're doing automated treatment planning using machine learning. We only need a CT image and contours. we can generate completely deliverable plans, and we've actually treated 2 patients using this exact method, patients that were treated, and we're having a study ongoing. From our retrospective study, we know that automated plans were equivalent to clinical, were better or equivalent to clinical, in 15 of 17 patients we did, and our prospective study is underway. Thank you for your attention. I'm going to pass it off to Tammy for questions and answers.
Okay, well, thank you both for a great presentation. We've had a lot of questions sent in, so we will just start and see how many we can get through in the remaining time we have. So, first question. What is typically the size of the data sets required for the model to be reliable to, say, greater than 99% success?
I can take that one. This is, as I think both of us have said, very hard to say in a general case. What you should do when training machine learning models is to have a validation or test set where you can test the model, and then you can look at kind of the result in terms of maybe the average result on this validation set or the worst case behavior. What we see is that for planning and segmentation, 100 patients or plans seems to be a good, a reasonable number. Tougher geometry needs more training data.
Okay. What are the advantages of the automatic planning in RayStation with deep learning in comparison with already existing automatic planning knowledge-based, such as rapid plan or auto planning in Pinnacle?
Yeah. When we developed this method, we have not compared. We don't have the accessibility, but the approaches are quite different in terms of what they do. But in terms of the results, I don't think there is any clinical study yet, but I think that would be very nice to see, since there are different approaches and they may have their strengths and weaknesses. I think one advantage of machine learning for planning is that the models can be shared. There's no sensitive data whatsoever, and they can just be distributed, or maybe there can be an app store or something. So I think it's very convenient for knowledge sharing.
I also want to add, I think one of the bigger advantages is we're doing effectively an optimization spatially without relying on things that were typically used for making plans, i.e. dose volume objectives from DVHs. So we don't rely on DVHs at all to be able to do this, and users don't have to specify any objectives at all. And so what we can hopefully do is better articulate how the dose is going to fall off or within a target, or how things are spared, and there's no iterative approach. So we're not taking a look at a database of, say, DVHs that were achieved before and trying to emulate them. The process is fundamentally different than that, and there's no objectives that need to be set by the user.
Okay, so are the likely dose distributions based on accelerator beam models for a specific clinic? Does the machine learning have to be done for every institution separately?
No, yeah, that's a great question. So the short answer is no. So I think you want to match, of course, site and modality and things like dose. If you have a treatment plan that was done at some nominal energy, like, say, for example, 6 MV for a VMAT case, even though there might be small differences between clinics in terms of how their B model performs, if we're talking about a LINAC-based treatment, for example, then those differences are extremely minor in terms of how this works, because the mimicking step in terms of generating the plan does incorporate your B model. The prediction is irrelevant, so the model will work, and then the mimicking will take advantage of the individual being characteristics at your center to generate the final deliverable plan. So it will all work out that way.
Okay, and if a model is trained on generic data, is it still possible to use any patient-specific information in creating the treatment plan?
Yes. So I think there are different ways to interpret this question, I think, but one answer here is that the machine learning model will adapt to the new geometry or new patient automatically. I mean, that's in the nature of machine learning. But also we can say here that the treatment plan generated that's exactly as any other plan in RayStation, so it can be processed if necessary. So if there is anything specific that needs to be added, maybe there's those constraints, then the user can continue to optimize. But one other way of reading this question is, could it be like patient history or some completely other information out there that the user knows about? So it's so to kind of enhance the machine learning, so it's not only image and RI specific. And I think that's an interesting topic where we can mix history with the other data. But I think that's not something we have at the moment.
Okay. Are there any privacy issues for the training data sets? Do you need local ethics committees, for example?
Yeah, that's another great question. So at the end of the day, as Fredrik was saying, we're building models based on data, so I think that solves a lot of the problems. But at the same time, this is a clinical work, so building those models you shouldn't need an ethics board approval because we're not actually doing research. So if this is part of clinical care, I think that's fine, and they're highly portable, as Fredrik said, because we're not actually sharing real patient data, so you can't go and get any information that will identify any single patient with any of the data that's needed for the model.
Okay, now the next question has been asked several times in various shapes and forms, but basically we have this sort of fear of people fear algorithms taking over their jobs. So how will machine learning in the clinic impact medical physics staffing?
So again, you go ahead, Fredrik. Yeah.
Basically, I think Tom had a great slide on this that described that in this study to combine machine learning with the human to see. I mean, I think, and we've seen other examples of that out in other studies outside oncology, that the humans together with machine learning models can generate great results. I mean, it's kind of augmenting the person to get this input from the algorithms. So I think that's what we're going to see.
Okay, so you mentioned cases where machine learning didn't work, for example, with the hip prosthesis. Is there any way to know beforehand whether the model will fail or perhaps struggle?
Yeah, I mean, so again, that's a great question. So I think again, it really all comes back down to data, because if you start mixing different types of data that you're building your model on, you're going to get some poor results. And so we did reconcile or reason that since the distributions are so different, that it doesn't make sense to lump them together. And so had we developed a model for, say, in this example, an entire model for patients with, say, double hip prosthetics, then we could have used it. We just didn't have a model available to us. But I think that is actually where there's still a lot of benefit for people who have clinical domain knowledge to be able to say that these things are different and they are impacting the dose distribution or not. And so I think that's a really good place where we will still be able to make a very large contribution. And we can make the systems much more sophisticated to be able to alert us when we see these variations in the input data. And we already do this now. So, you could also say, I find these patients to be an outlier from this entire group of patients in a database. And so, but someone needs to check that, right? And someone with some clinical knowledge needs to be able to say what's going on. But yeah, I mean, this is always going to be the case because, if we give it the wrong data, we're going to get bad results.
Okay. There's a question here. What's the planning time of automated machine learning compared to clinical planning time?
Yeah, so I can answer on the automated machine learning plan. So for each plan, it would be 1 minute roughly for the machine learning part when you apply the model, and then it would be the optimization time, which would be for a VMAT maybe 3, 4, 5 minutes, depending on the size of the case. Then that's when applying. So that's when you run it. And of course, the training can take hours and hours, but it's done offline, so it can be on a standalone hardware, and it can be done over weekends or evenings and so on. So when you actually run it online, it should be in a matter of minutes. Then the real clinical planning time, I mean, Tom has better knowledge about that.
Yeah, I mean, we are really talking minutes. So when we've been running it, again, too, we haven't been using clinical hardware for any of the dose prediction steps. So it's actually really hard to say. But I mean, the numbers that Fredrik was talking about are in line. We can actually do things. So it's actually pretty interesting, which is also maybe not totally intuitive. But when we did our technical study on oropharynx, that went much faster, only because the actual volume that's irradiated is much smaller than, say, in something like prostate. So we could actually plan oropharynx, although deemed much more complicated, faster. And so that's actually really interesting and provocative in that what we deem right now as being complicated to a machine does not, right? It just sees it all being the same. So that's actually great. So again, too, prostate might be like less than, they'll probably be less than 10 minutes, and this will just, just keep getting better. And as Fredrik said, the bulk or the heavy lifting is done offline. So, while you're building the model. So that time is, in effect, doesn't really matter. We're not going to be producing models every day. Although we could build a new model every night. That would be completely feasible, I think.
Okay, I think we have time for one final question. So, is the machine learning contouring and planning, is it CE marked and or F10K cleared yet?
No, so this will be part of the 8B release in December. So that will be kind of the standard process to get it cleared in the markets. And I think depending on which market, of course, it will take everything from weeks to a few months. But I'm not a regulatory expert, so I can't answer that better, unfortunately.
Okay, great. Well, we are coming up to the end of the webinar now, so thank you to everyone in the audience who asked a question. Now, I'm aware we have more sent in than we could cover, so if your question wasn't addressed, you'll be contacted by email with an answer. If you'd like to watch the webinar again or recommend it to a colleague, it will soon be available in the webinars section on the Physics World website. And finally, thanks again to Fredrik and Tom. Thank you to everyone who's joined us today. And this webinar is now over.